Okay, so it's time to talk about sound. We've done an overview of all the different terms and features of waves, and so now it's time to look at sound, which is one type of sound is a wave, a specific type of wave. We've already talked about it a bit. We said that sound was a mechanical wave, and that means that it needs material in order to travel. So there is no sound in outer space where where it's a vacuum, okay, where there's no air. Sound travels best in solids, and by best we mean fastest. It travels next best in liquids, and then next fastest in gases, and not at all in a vacuum. Why is that? Because really sound is, it's a, down here, it's a longitudinal wave. Okay, a mechanical wave and a longitudinal wave. And remember, a longitudinal wave was the one where we showed the molecules just as straight lines. And so what happens with the sound is the source, whether it's my vocal cords or the top of a drum or a guitar string, the source pushes on this first molecule, and it pushes it closer to the second, closer to the third, and then it releases it and comes back, and then it pushes it again. So what happens is this pushing in, spreading out, pushing in, spreading out, gets passed down the medium. So obviously the closer the molecules are together, the more dense the material, the easier it is to pass this vibration along. So that's why solids, it can move fastest through solids, because the molecules are very close to each other and touching. More difficult in liquids because the molecules are moving all around. Even more difficult in gases because they're moving all around and more spaced apart. Okay? So the more dense the medium, the faster it travels. And I think I said it when we were first starting waves, it's why putting your ear to a train track works. Okay? It's not that, so it travels fastest in solids. So when you put your ear to a train track, as opposed to a person who's standing up just listening, the sound wave will get to you through the train track quicker, which means it has less time to lose its energy to its surroundings, less time to dissipate its energy to its surroundings than through air, because it takes longer to reach you in air. There's a longer amount of time where it can lose energy. And remember, we did that, I showed you a wave that starts out nice and big, but then as it goes along, it loses amplitude because it's losing energy. Okay, so the quicker it can travel, the quicker it'll get to you before it gets to the point where the energy is so weak that you can't hear it anymore. All right. Now, if we can calculate the speed of sound in air. Okay, this formula only works in air. There are charts if we want to look up the speed of sound in liquids and gases and solids. And that chart in your textbook is on page 387. But in air, and remember, the speed of a wave in a medium is constant. So if we calculate the speed of sound in air, which is a particular medium, and we're assuming the air is just normal, it doesn't have any kind of particles in it, then the speed is equal to 331 meters per second plus 0.59 meters per second degrees Celsius times T, where T is the temperature, because the speed of sound in air depends on the temperature. Now, I don't know if you got to this in chemistry yet or not, but temperature is just really a measure of the kinetic energy of the molecules. So the higher the temperature, the more the molecules are moving. And the more the molecules are moving, the easier it'll be to pass the vibration. The lower the temperature, the less the molecules are moving. And remember, in air, the molecules are all spread out, so if they're not moving very fast, it's going to be harder to pass the vibrations along. So the temperature has to be in Celsius. You just put it in here, multiply it by 0.59, and then add it to the 331. So if it's 0 degrees, the speed of sound at 0 degrees Celsius is just 331. If it's 100 degrees, then this term will be 59. You'll add it on here and you'll get 390 meters per second. If the temperature is not given in the question, then you are to assume room temperature. And room temperature, in case you were wondering what it is 20 degrees. Okay, so whenever you're not given a temperature in the question and you need the speed, then you use this equation and you assume 20 degrees. So let's find the speed for 20 degrees. It'll be 331 meters per second plus 0.59 meters per second degrees Celsius times 20. So times 10 would be 5.9, so times 20 is 11.8. So this is going to be equal to 342.8 meters per second. Okay, so it's just going to be that easy. This evening or today you will have some practice questions with this equation. But remember the speed of sound, this is only for air. If you're looking for it in water or in steel, you have to look it up on the chart on page 387, okay? The speed of sound in air is actually also dependent upon pressure. The higher the pressure, the faster it will go. But so this temperature is, or this equation is based on like standard atmospheric pressure. All right, a couple more things about sound. One is the two terms echoes and there's something on my tip of my pen. Reverberations. Now I am 100% sure you've all heard of echoes. Not so sure you've heard of reverberations, but I think what you've been calling some echoes would be reverberations. Both are caused by reflection. When sound wave travels, hits a surface, and comes back. Okay? You've heard an echo probably, maybe if you've been at the top of a cliff or a drop and there's like another hill on the other side, you can maybe hear your echo off of it. You've maybe heard something similar if you've ever, in a room in your house, if you've ever cleaned out all the furniture to maybe paint the walls or put down new flooring. The room, we would say the room echoes, right? It doesn't normally when all the furniture is there. So both of these are a reflection of the wave off a surface that's some distance away. But for an echo, the surface has to be at more than 17 meters away. So really, you probably don't have a room in your house that you're going to hear an echo from. Reverberations happen when the reflecting surface is less than 17 meters away. So really what you would be hearing in most rooms would be a reverberation. Maybe in our large gym we would hear an echo, but most of our other rooms it would be a reverberation. Outside, that's a different story. Okay, so when you're dealing with echoes, the thing to remember is if it says you shout and then you hear the sound like 4 seconds later, remember that's the total. That means it took 2 seconds to go down and 2 seconds to go back. And that becomes important if it's asking you how far away is the reflecting surface, because you're going to have to divide the time by 2 or divide the distance by 2 when you find it, because it's a down and back thing. Okay, so just be careful when you're doing echoes and reverberations, because lots of times you're dealing with the time down and back, but you're only looking for the distance one way. All right, next is loudness. Back when we first talked about sound, we said that loudness has to do with the energy the sound is carrying, the amplitude of the wave. Okay, so the bigger the amplitude of the wave, the louder the sound. And we often also call sound the loudness the intensity of the sound. Okay, now we're going to run out of time, so we'll come back to loudness in the next video.